Welcome to Night Cosmos Sleep. Tonight, we will move very slowly toward a question that may seem far away, yet lies behind every point of light we have ever seen in the sky. How did the first stars in the universe begin to shine? When we look up at the night sky, we often feel as if the stars have always been there, as though the universe has been sparkling with light since the moment it was born. But in truth, there was once a very long time with no sun, no Milky Way, and no clusters of stars scattered across the darkness. Back then, the universe was mostly expanding space, very light clouds of gas, and gravity quietly pulling things closer together little by little. Then, somewhere in that vast darkness, one region of gas began to grow denser. It slowly collapsed darkness inward, heated up, became heavier, deeper, until its center grew hot enough for the first nuclear fire to awaken. Not fire like the kind we know on Earth, but the light of a star, the first source of light that opened the true dawn of the universe. In tonight's journey, we will not rush through difficult numbers or heavy terms. We only need to imagine the universe as a very large room that had gone without starlight for a very long time. Then, somewhere far away, the first lamp was turned on. From that small light, the later stories slowly began. Galaxies, planets, the night sky, and even the materials that are very close to us today. The elements in the air we breathe, in water, in rock and soil, and in the human body itself. So before there were the familiar stars we see today, what had that darkness been preparing? And what finally made the first star in the universe truly begin to shine? Imagine you are in a very dark room where everything around you becomes quiet and slow. You look out the window, and somewhere in the sky, a few tiny points of light seem to stand still. Maybe one is a star, maybe another is a planet reflecting light. For human beings, the night sky has almost always been connected with points of light. Whether we live in a brightly lit city or in a place where the darkness is truly deep, we still understand that the stars are out there. They may be hidden behind clouds, washed out by city lights, or too far away for our eyes to see clearly, but we know they are there. That familiar feeling makes it easy to assume that the universe has always been a place with stars. But if we go far enough back in time, that sky disappears. Not because the stars are hidden, but because the stars have not yet been born. The universe already existed, but there were no great balls of gas creating light deep inside their cores. There was no Sunday. There was no Milky Way as a home to hundreds of billions of stars. There were no bright galaxies scattered across the darkness. The universe at that time was like a vast room before the first lamp had ever been switched on. That room was not empty, because darkness does not mean nothing exists. Before there were stars, the universe still had matter. It still had gas. It still had gravity, the pulling force that makes matter move closer together. Everything was simply much more basic than it is today. Most of the ordinary matter back then was hydrogen and helium, the two lightest gases. They had not yet formed planets. They had not yet formed stars. They had not yet become the glowing structures we are used to seeing in modern images of space. After the universe's extremely hot beginning, often called the Big Bang, everything slowly expanded and cooled. The first light from that early time was not starlight. It belonged to a universe that was still hot and dense. Then, as the universe cooled, a long period appeared, quieter and darker. Space already contained matter, but there were no new sources of light. It was like a room with everything already inside it, but with no lamp turned on yet. In that darkness, the important story began with very tiny differences. Gas in the universe was not spread out perfectly evenly everywhere. Some regions were just a little denser. Other regions were just a little thinner. These differences were so small that they might seem almost meaningless. But gravity does not need a dramatic beginning. It only needs one place to have slightly more matter than the area around it. That place begins to pull in more gas. As more gas gathers, it becomes heavier, and as it becomes heavier, its pull becomes stronger. Little by little, A faint region of gas in the darkness began to become something special. It did not shine yet. It was not a star yet. It did not have the beautiful shape of the nebulae we see in modern photographs. But it was already different from the space around it, because more matter was beginning to gather there. From one small imbalance, the universe began preparing a place for something much greater. You can think of water vapor gathering on a cold window. At first, the vapor is almost invisible. It is in the air, thin and light. But where the surface is cold enough, tiny droplets begin to cling to it. A soft haze appears, then slowly becomes clearer. There is no sound announcing the change, no sudden explosion, but the surface has already transformed. In the early universe, hydrogen and helium gathered slowly in a similar way, held together by the pull of gravity. Of course, a cloud of gas is not yet a star. It is only the first step. To become a star, that cloud must keep collapsing inward. Its center must become denser and hotter. Matter must be pressed deeper and deeper until the inner core reaches a special condition. Hydrogen can begin producing energy. But that moment still lies ahead. For now, we only need to see the door beginning to open. Before there was light, there was gas. Before there were stars, there was a slow gathering in the dark. That is why the question of the first star is not only a distant question for scientists. It touches something very basic. What feels familiar to us today once had a beginning. The star-filled sky was not always there. Starlight was not present from the start. The universe once passed through a long stretch of time without the points of light we still see every night. If you look out the window now and see a few distant stars, they may appear small and still. But behind them is a history longer than any human story. There was once a time when no lights like that existed at all. Then, somewhere far back in the past, a region of gas began to gather, collapse inward, heat up, and prepare for the first moment when the universe could create its own starlight. Before there were stars, the universe was not a dead and empty silence. It was a dark room, already holding the ingredients. There was gas, there was gravity, there was time. And inside that darkness, the first steps toward light had already begun. Before the first stars appeared, the universe once had a very different kind of light. It did not come from a star. It did not come from a galaxy. And it was not like the light we see when we look up at the night sky. It was the leftover light from a very distant time, when the universe had cooled just enough for light to travel through space without being constantly blocked. To understand this, we can imagine a room filled with thick white fog. There may still be a lamp in that room, but because the fog is so dense, the light scatters everywhere. You cannot see very far. You cannot clearly see the wall. You cannot clearly see the objects in front of you. The light has not disappeared. It is simply trapped, redirected again and again, making the whole room appear cloudy and opaque. The very young universe was once like that, but on a scale far greater than anything we can picture easily. At that time, space was not like the quiet emptiness we often imagine. It was hot, dense, and filled with tiny particles constantly moving. There were particles with a negative electric charge, called electrons. There were particles with a positive electric charge, called protons. There was light, there was energy, and there were countless collisions happening everywhere. Every time light tried to travel far, it would easily run into free electrons and get redirected. So even though the universe at that time was very bright in the sense that it contained a great deal of radiation, it was not yet transparent. Light was almost trapped inside a hot fog. It could not travel straight across enormous distances, the way starlight travels through space today. Then the universe continued to expand. When something expands, it usually cools down, and the universe did the same. As space stretched wider, the average temperature dropped. When everything was still too hot, electrons could not attach steadily to protons. It was like two tiny particles coming close together, only to be pulled apart again by the energy around them. But when the universe became cool enough, electrons began to combine with protons, forming the first atoms. An atom can be understood simply as a very tiny structure of matter, with a central part and electrons around it. Once electrons had attached to protons, they were no longer drifting freely in such large numbers. This was extremely important, because light was no longer being blocked over and over again. The hot fog of the universe began to clear, space became more transparent, and from that moment, light could travel far. That was when this ancient light was released. That light has traveled through the universe for more than 13 billion years. During that long journey, space kept expanding, and as space expanded, the light itself was stretched. You can imagine a wave drawn on a rubber band. If you stretch the rubber band, the waves also move farther apart. With light, the distance between these wave peaks is called wavelength. When the wavelength becomes longer, the light becomes colder, weaker, and gradually shifts into forms that human eyes can no longer see directly. Today, that ancient light no longer appears as ordinary visible light. It has been stretched into a very faint kind of wave, with a wavelength longer than the light our eyes can see. That kind of wave is called a microwave, because it is left over from the very early universe, and because it reaches us from nearly every direction. Scientists call it the cosmic microwave background radiation. The name may sound difficult, but its meaning can be understood quite simply. Radiation means energy traveling in the form of light or waves. Background means it is like a faint layer of light behind everything else. Microwave means it is a kind of light that has been stretched so much that human eyes cannot see it. And cosmic tells us that it does not come from one individual star, but from the early universe itself. The most important point here is this, that light did not come from stars. It existed long before the first stars. It was the light of a universe that had just changed from being cloudy and opaque to being transparent. It was like the light left behind after the first fog had cleared. Not the lights of a city, not a candle in a room, but a trace from the entire universe in its earliest age. This difference matters. When we hear the phrase, first light, it is easy to think of the light from the first stars. But in reality, the history of the universe has many layers of light. There was the ancient light released when the universe became transparent. And much later, there was the light of the first stars when the original gas gathered together, collapsed inward, heated up, and began nuclear reactions inside stellar cores. In other words, the universe did not go straight from the Big Bang to a sky full of stars. After the hot and cloudy period, it cooled, became transparent, and then entered a long stretch of time without stars. The ancient light still existed and continued to travel through space, but new sources of light, such as stars and galaxies, had not yet been born. This is easier to picture if we return to the image of the room. Earlier, the room was full of fog, so light could not travel far. Later, the fog slowly cleared, the air became more transparent, and if there had been a lamp, its light could have spread through the room. But the problem was that no lamp had been turned on yet. The room was ready to be illuminated, but the true source of light had not appeared. The universe, after it became transparent, was similar. It was no longer opaque as before, but it still had no stars. There was no Sunday. There were no large galaxies. There were no brilliant star clusters. There were no planets orbiting warm sources of light. Space at that time mainly contained very light gas, mostly hydrogen and helium. Hydrogen is the simplest and lightest element. It is like the first building block for many structures in the universe. Helium is a little heavier than hydrogen, but it is still a very light element. In the young universe, these two elements made up most of the ordinary matter. Elements more familiar to life on Earth, such as the carbon in living bodies, the oxygen in the air, or the iron in rocks and metals, were almost not present in large amounts yet. They had to wait for the first generations of stars to create them later. Because there were no stars yet, this period is called the Cosmic Dark Ages. The name may sound cold and empty, but it should not be understood as a dead silence. Dark here simply means that there were not yet concentrated sources of light like stars. Inside that darkness, matter was still moving, gas still existed, gravity was still working, and the first seeds of cosmic structure were quietly growing. Gravity is the force that pulls matter together. On Earth, it gives things weight and makes an object fall to the ground when we let it go. In space, it also makes regions with more matter pull in more material from around them. If one place is slightly denser than its surroundings, it can draw in more gas. As it draws in more gas, it becomes denser, and as it becomes denser, its pull becomes stronger. The earliest differences in the universe may have been very small. Some places had just a little more matter than the areas around them. Other places were a little thinner, but over a very long time, those tiny differences became important. They were like faint folds in a large piece of fabric. At first, almost no one would notice them, but given enough time, those folds could guide matter in one direction, gathering it into denser regions. Here, we need to mention a kind of matter that does not shine, does not reflect light, and, even today, has not been identified exactly in terms of what particles it is made from. We cannot see it directly with our eyes or with ordinary telescopes, but we recognize it because its gravity affects stars, galaxies, and gas. This invisible kind of matter is called dark matter. Dark matter is not called dark because it is evil or mysterious in a supernatural sense. It is dark simply because it does not give off light for us to see. In the early universe, dark matter played a role like an invisible scaffold. It helped create the first regions of gravity where ordinary gas could fall in. If we looked only with light, we would not see that scaffold. But if we looked at how matter moved, we would know it was there. Hydrogen and helium gas gradually fell into these gravitational regions, but falling in was not enough to create a star. The gas had to gather, become compressed, heat up, and also lose some of its energy so it could collapse even deeper. If the gas was too hot, the pressure inside it would push outward and resist the collapse. So for a cloud of gas to become a place where stars could form, it had to find a way to cool down. In the universe today, gas has many more ways to cool because there is cosmic dust and many heavier elements created by earlier generations of stars. But in the first universe, everything was much simpler. The gas was mostly hydrogen and helium. That made the birth of the first stars more difficult, slower, and dependent on very special conditions. But difficult does not mean impossible. In that long darkness, regions of gas continued to be pulled together. The areas that were slightly denser became denser still. The first primitive clouds began to form. They did not shine. They did not have the beautiful shapes of the nebulae we see in modern astronomical images. They were only extremely distant, extremely ancient masses of gas, quietly falling into deeper regions of gravity. From the outside, the universe might have seemed silent, but inside that silence, a vast process was unfolding. The universe had passed through its hot and opaque stage. It had become transparent. Ancient light had been released. Then the long darkness began, not as an ending, but as a very long preparation before dawn. We can think of that ancient light as the newborn photograph of the universe. It tells us what the universe was like before stars existed. And the first clouds of gas were signs that the universe was preparing to enter a new state. Matter was no longer spread almost evenly everywhere. It was beginning to gather. It was beginning to form places. It was beginning to move toward the first structures. And within that process, the story of the first stars truly begins to become clearer, not with a sudden beam of light, but with dark regions of gas quietly collapsing inward. Not with a brilliant sky, but with a few tiny seeds of gravity hidden deep inside a young universe. Before the first lamp could be turned on, the room had to become transparent. Before the first star could shine, the universe had to cool enough for ancient light to travel freely. And after that, it entered a long dark age, where gas, gravity, and time prepared together for the first moment of starlight. Somewhere in that darkness, The first gas clouds were beginning to gather. They were not shining yet, they were not stars yet. But inside them, the universe was taking one very slow step toward dawn. After the ancient light was released, the universe became more transparent. Light was no longer constantly trapped inside the hot, dense layer of matter as it had been before. It could travel farther, move through wider stretches of space, and leave behind a very faint trace that humans can still measure today. Imagine a room where the fog has just cleared. Before, the fog was so thick that light could not travel very far. Now, the air has become clearer. If there were a lamp, its light could spread across the whole room. But the problem was that, at that moment, no lamp had been turned on yet. The universe after its earliest stage was much like that. It had become clear enough for light to pass through, but there were still no stars to create new light. There was no Sunday. There were no bright galaxies. There were no great star clusters. There were no planets orbiting a warm source of light. The ancient light was still there, but it was only the leftover light from the very early universe. Starlight had not yet appeared. That period without stars is called the cosmic dark ages. The name may sound cold, but it should not be understood as meaning the universe was empty. Dark here simply means there were no light sources like stars and galaxies yet. Matter still existed. Gas was still present. Gravity was still at work. And inside that silence, the first preparations for the birth of stars were beginning. At that time, ordinary matter in the universe was mostly made of two very light kinds of atoms. The first was hydrogen, the simplest element. The second was helium, a little heavier than hydrogen but still very light. Elements familiar to life, such as the carbon in our bodies, the oxygen in the air, or the iron in rocks and soil, were almost not present in large amounts yet. The reason is that those elements needed to be made inside stars. But at this point, there were no stars at all. So the universe back then was very simple. It had hydrogen, helium, ancient light slowly weakening, and gravity. With only those things, it had to begin building the first structures. Gravity can be understood simply as the force that pulls matter closer together. On Earth, it makes an object fall when we let it go. In space, it makes regions with more matter pull in more material from around them. At first, the differences between regions were not large. Some places were only a little denser than their surroundings. Other places were a little thinner. But if one region was slightly denser, it could attract more matter. As it attracted more, it became even denser. As it became denser, its pull became stronger. In this way, a very small difference could grow larger over time. You can imagine a tabletop with a shallow dip in the middle. If a few drops of water fall onto that surface, they will naturally tend to flow toward the dip. Once more water gathers there, the larger drop can more easily collect smaller drops around it. In the young universe, slightly denser regions worked in a similar way, but through gravity and over a much longer period of time. However, the matter we can see is not everything. There is a kind of matter that does not shine, does not reflect light like familiar objects, and cannot be seen directly with ordinary telescopes. Scientists know it exists because its gravity affects the way galaxies, gas, and light move. In simple terms, we do not see it, but we see its effects. That kind of matter is called dark matter. The word dark here simply means it does not give off light for us to observe directly. It is not something mystical in an imaginary sense. In the story of the first stars, dark matter is extremely important because it created regions with stronger gravity. These regions were like invisible wells in space, places where hydrogen and helium could fall in and gather. Without those gravitational regions, the original gas would have had a much harder time gathering enough material to form stars. The universe was expanding, and the gas was light and thin. It needed places that were deep enough in gravity to hold the gas, pull it inward, and make it denser over time. For a cloud of gas to become a star, it had to keep contracting inward. When gas is compressed, it heats up. When it heats up, it creates pressure. Pressure can be understood as the outward push of hot gas. For example, when the air inside a balloon gets hotter, it wants to expand more strongly. A cloud of gas in space behaves in a similar way. If it becomes too hot inside, it pushes back against the gravity pulling it inward. So, in order to keep contracting, the gas cloud had to lose some of its heat. Today, star-forming clouds have many ways to cool down because space now contains dust and many heavier elements made by earlier generations of stars. But in the first universe, there was almost only hydrogen and helium. That made cooling much more difficult. Fortunately, hydrogen had one small way to help. Sometimes, two hydrogen atoms could join together as a pair. That pair is called a hydrogen molecule. When hydrogen molecules were present, the gas cloud could release some of its energy more easily. Because of that, it could cool a little, giving gravity a chance to pull it deeper inward. Not every place could do this. Only regions with enough matter, enough gravity, and enough ability to cool could come close to forming stars. For that reason, the first stars did not appear everywhere in the universe at the same time. They probably formed here and there, in special places where all the necessary conditions came together. We can imagine this stage like a field before sunrise. From far away, everything still looks dark. There is no sunlight yet, no clear color. But under the soil, seeds have already begun to take in water. Young roots have already begun searching for a path. The surface remains quiet, but beneath it, the preparation has begun. The young universe was much the same. From the outside, there was no starlight yet, but in deeper gravitational regions, hydrogen and helium were gathering. The first primitive gas clouds were becoming denser. Their central regions were beginning to heat up. Some hydrogen molecules helped the gas lose a little heat, so the collapse did not stop too early. Everything happened very slowly. There was no great explosion announcing that a star was about to be born. There was no flash of light right away. There was only matter falling inward, temperature rising little by little, and heat being released in small amounts. Over a long stretch of time, the center of a gas cloud could become far denser than it had been at the beginning. That was an important step on the path toward creating the first star. Before there could be a true star, there had to be a region of gas dense enough. Before that gas could become dense enough, it had to be pulled into a place with strong gravity. Before it could collapse more deeply, it had to find a way to cool. All of these steps happened during the Dark Ages, when the universe still did not have the familiar points of light we see in the sky today. So that dark period was not a meaningless emptiness. It was a time of preparation. It was when the first ingredients were gathered. It was when gravity built the places where stars could be born. Without this stage, there would have been no first star. Without the first star, there would have been no first heavy elements. And without those elements, much later on, there would have been no rocky planets, no oceans, no air as we know it, and no living bodies made from complex elements. Seen this way, the Dark Ages were not simply darkness. They were the opening part of a very long story, when things had not yet appeared clearly, but the most important conditions were already beginning to form. Somewhere in the young universe, a gas cloud was becoming denser. It was not shining yet, it was not a star yet, but inside it, matter was falling deeper inward. The temperature was rising. Pressure was trying to push outward, while gravity continued to pull inward. With the help of very simple cooling processes, the gas cloud could keep contracting further. Then one day, if its center became hot enough and dense enough, nuclear reactions would begin. At that moment, hydrogen would no longer be just gas drifting in the dark. It would become the fuel of a star. And from a dark region that once seemed unremarkable, the first starlight would finally have a chance to be born. Before the first stars could shine, the universe needed a place to begin. Not a special place in the sense that it already had light or a beautiful shape, but simply a region of space that was slightly different from its surroundings. There was a little more matter. Somewhere else, there was a little less. That difference was extremely small. so small that if we tried to imagine it with the naked eye, we would almost not notice it. But for the universe, sometimes a tiny difference like that is enough for the story to begin. Think of a very still lake. From far away, the surface of the water may look completely flat. But if we come closer, we can still see very faint ripples. Those ripples do not change the lake immediately, but they show that the stillness is not absolute. The early universe was not perfectly even everywhere either. Some regions were slightly denser, some regions were slightly thinner. Those tiny differences became the starting points where matter would slowly begin to gather. In science, these slightly denser or slightly thinner places are called density fluctuations. But we do not need to keep that term in mind for too long. We only need to understand it simply. Density means how thick or thin matter is within a region. If one place has more matter in the same amount of space, it is denser. If it has less matter, it is thinner. And those slightly denser regions at the beginning became the places where gravity could work a little more strongly. Gravity is the force that pulls matter closer together. On Earth, it makes an object fall when we let it go. In space, it makes regions with more matter pull in more material from around them. At first, that pull may have been very weak, but it did not need to be strong right away. It only needed time. A slightly denser region would attract a little more matter. As it attracted more, it became even denser. As it became denser, it could attract even more. In that way, a tiny change at the beginning slowly grew larger. You can imagine a few drops of water falling onto a tabletop with a slight dip in it. If the table were perfectly flat, the water might spread out. But if there is a small hollow, the water will naturally flow toward it more easily. Once more water gathers there, that spot can hold even more small drops around it. In the young universe, slightly denser regions were like those shallow dips. They did not shine. They did not stand out. But they were places where matter could gather more easily. This helps us understand why the universe did not remain forever as a thin layer of gas spread across space. Space was still expanding, but gravity was quietly pulling matter together in places that were slightly denser. Both processes were happening at the same time. On one side, the universe was stretching outward. On the other, in some smaller regions, matter was beginning to collect. From those gathering regions, the first gas clouds would slowly form. Not everything we are talking about can be seen directly. There is a kind of matter that does not shine, does not reflect light, and does not appear clearly through ordinary telescopes. We do not see it the way we see a star, but we know it is there because its gravity affects the way gas, galaxies, and light move. This invisible kind of matter is called dark matter. Dark matter does not need to be understood as something mystical. It is dark simply because it does not give off light for us to see. In the early stage of the universe, it was very important because it created regions with stronger gravity. Those regions were like invisible depressions in space. Ordinary gas, mostly hydrogen and helium, could fall into them, be held there, and gather in greater and greater amounts. Hydrogen and helium were the two lightest elements in the young universe. Hydrogen was the simplest, while helium was a little heavier. Elements more familiar to life, such as carbon, oxygen, or iron, barely existed in large amounts at that time because they needed to be created inside stars. But at this point, stars had not yet been born, so the universe was beginning with very simple ingredients: light gas, gravity, dark matter, and time. A slightly denser region did not immediately become a star. At first, it was only a place where more matter gathered. Gas fell into that region, making the center thicker. When gas is compressed, it heats up. But if the gas becomes too hot, it tends to push outward. We can imagine this like the air inside a balloon. When it heats up, it wants to expand. That outward push is called pressure. To keep collapsing inward, the gas cloud needed to lose some of its heat. If it could not lose heat, it would grow hotter and have a harder time contracting more deeply. In today's universe, star-forming clouds have many ways to cool down because space already contains dust and heavier elements that help. But in the first universe, everything was still very simple. There was almost only hydrogen and helium, so cooling was much more difficult. Fortunately, hydrogen could help in a small way. Sometimes, two hydrogen atoms could join together into a tiny pair. A group of atoms connected together like this is called a molecule, in this case, a hydrogen molecule. These hydrogen molecules could help the gas cloud release a little energy into space. As it lost some energy, the gas cloud cooled slightly, and gravity could continue pulling it deeper inward. This process happened very slowly. There was no great explosion. There was no beam of light appearing right away. There was no brilliant scene like the ones we see in modern astronomical images. There were only regions of matter that were slightly denser, gathering more gas bit by bit. The center became thicker. The temperature gradually rose. The gas was being pulled inward while also trying to push outward because of its heat. And if cooling worked well enough, gravity could win one more step. We can imagine this stage like a field before dawn. From far away, everything is still dark and quiet. There is no sunlight yet, no clear color. But beneath the soil, seeds have already begun to take in water. Young roots have already begun searching for a path. Someone standing outside may not see anything changing yet, but inside, the preparation has already begun. The young universe was the same. There was no starlight yet, but in the deeper regions of gravity, gas was gathering and slowly changing. The important point is that the first stars did not appear everywhere at the same time. The entire universe did not suddenly light up like a city when the power comes on. Only certain special regions had the right conditions: enough gas, strong enough gravity, a way to cool down, and enough time for the center to become denser. In places like those, the path toward the first star truly began to open. When we think of it this way, the first light of the stars was not a surprise that appeared from nowhere. It was prepared for a very long time in silence. Before there could be light, matter had to gather somewhere. Before there could be a hot core, there had to be a gas cloud dense enough. Before a star could begin its life, many small steps had to happen in the dark. That is why those slightly denser regions at the beginning were so important. They were like quiet starting points for every structure that would come later. Without them, gas would have had difficulty gathering. Without gathered gas, there would be no dense cloud. Without a dense cloud, there would be no hot core. And without a core hot enough, the first star could not shine. Somewhere in the young universe, a slightly denser region was pulling more matter into itself. At first, that change was very gentle, almost unnoticeable. But after a very long time, it became a place deep enough in gravity to hold gas. Hydrogen and helium began to gather there, slowly and quietly. From those small movements, the first star-forming clouds began to take shape, and from those clouds, the universe moved closer to the first moment of starlight. After a very long time, the first gas cloud began to change in its deepest part. On the outside, everything was still extremely thin. Hydrogen and helium were still spread across a large region of space, so faint and diffuse that they almost had no clear shape at all. But at the center, where gravity was stronger, matter began to gather in greater amounts. Layer after layer of light gas fell inward, slowly and quietly, like night mist gradually collecting at the coldest point on the grass. At first, this change was very hard to notice. No light burst out. No explosion occurred. There was no brilliant image like the astronomical photographs we often see. There was only a region of gas becoming thicker in the middle. But that denser region was extremely important because it was where the cloud began to create the first seed of a star. As gas continued to fall toward the center, the middle of the cloud became heavier and heavier. The heavier it became, the more matter it pulled in from around it. This process was like a small snowball rolling slowly across soft snow. At first, it is very small, but as it rolls through more layers of snow, it gathers more material, grows larger, becomes heavier, and then becomes even better at gathering more. Inside the first gas cloud, the central region grew in this same slow way. At this point, what was forming in the middle of the cloud was still not a true star. It did not shine steadily like the sunday. It did not yet have a powerful source of energy inside, but it was no longer thin gas drifting freely through space. It was a growing hot core, being fed by the cloud around it. Scientists call this stage a protostar. In simpler words, a protostar is a star in the process of forming, like a seed that has begun to grow but has not yet become a tree. Imagine a dark kitchen before a fire has been lit. The wood has already been gathered. A little warmth has begun to appear because everything has been placed closer together. But the real flame has not started yet. The kitchen has not truly brightened. A protostar is similar. It already has the material. It already has heat. It already has a growing center. But the real inner fire, the thing that allows a star to live and shine for a long time, has not yet begun. As matter falls deeper inward, it is compressed. And when it is compressed, it heats up. This can be understood through a very familiar example. When we use a hand pump to inflate a bicycle tire, the pump tube can become warm because the air inside is being compressed. In the first gas cloud, hydrogen and helium were also compressed as they fell toward the center. Because of that, the core in the middle gradually became hotter. But at this stage, that heat mainly came from matter being pulled inward and squeezed together, not yet from the inner reactions of a mature star. A true star needs more than that. Its core must become hot enough and dense enough for hydrogen to begin fusing into helium, releasing energy from within. Before that happens, the protostar is still only a seed preparing itself. It warms up, grows larger, takes in more material, but it does not yet sustain its own light like a complete star. This is the important point, and we can remember it simply. A protostar is the stage before a real star truly lights up. Around the protostar, the gas cloud continued to move. Some material fell directly into the center. Other material circled around the core before falling deeper inward. When a large mass of gas contracts, even a very slight initial spin can become more noticeable. It is like a figure skater spinning. When the skater pulls their arms closer to their body, the spin becomes faster. In space, something similar happens. As gas moves closer to the center, its rotation becomes easier to see. The region of gas spinning around the core can be called a gas disk. In more scientific language, it is an accretion disk, but we only need to understand it simply. It is a ring of material rotating around the protostar, slowly falling inward. Accretion means adding material little by little. The image is similar to water swirling around the mouth of a funnel before flowing down. Through this stream of material, the protostar continues to grow. This scene does not need to be imagined as something violent. It is much quieter than that. In a dark and extremely distant region of space, a large cloud is collapsing inward. At the center of that cloud, a small core is slowly heating up. Around that core, light gas rotates gently, falls inward, and makes the center heavier. There are no planets nearby. There are no living beings to witness it. But nature is still working, steadily and patiently. As the protostar grows larger, it begins to affect the region around it. As the core becomes hotter, it may give off a little heat and faint light. That light is not yet the strong, steady light of a true star. It is more like the gentle warmth from a fire that has not fully caught. That warmth can slightly change the gas near the center, making the inflow of gas less perfectly calm than before. But during this stage, gravity is still the most important force, because it continues pulling more matter toward the growing seed. Not every protostar is the same. In some places, the gas cloud provides a great deal of material, allowing the core in the middle to grow more strongly. In other places, the cloud may split into several smaller parts, creating several different seeds. Scientists are still studying how large the first stars usually became. But to follow the story clearly, we only need to hold on to one main idea. Before a true star can appear, a hot core must first form inside a cloud of gas. What makes this stage beautiful is that it exists between two states. Before it, everything was only thin gas in the darkness. Later, there would be a star shining with energy of its own. The protostar stands between those two things. It is not yet complete light, but it no longer belongs entirely to the darkness. It is like a lamp that has already been assembled, already wired, already prepared with a source of power, while the final switch has not yet been turned on. At this point, we can hold a very gentle image in mind. A vast cloud in the young universe, a small core slowly heating at its center, and streams of gas gradually carrying more material inward. There is no need to rush. There is no need for tension. The universe is doing this in a very slow way, as if preparing its first lamp after a long night. Then, eventually, the protostar becomes much heavier and much hotter than it was at the beginning. Its deepest part is squeezed more strongly. The particles inside move faster. The temperature continues to rise, but one more step is still needed. To become a true star, the inner core must be hot enough and dense enough for hydrogen to begin fusing into helium in a stable way. When that happens, its source of energy will no longer come only from gas falling inward, but from the reactions inside the core itself. That moment is getting close, but there is no need to hurry toward it yet. Before the first star lit up, the universe went through a very quiet stage like this, a seed of a star growing inside its own cloud. There was no explosion announcing it. There was no brilliant light right away. There was only gravity, layers of gas falling inward, and a small core slowly heating in the dark. From a primitive cloud, the first protostar appeared in this way. Not through a miracle, but through the slow gathering of matter, heat, and time. It was the first promise of light, a point that was not fully shining yet, but was no longer invisible thin gas as before. As its core continued to heat up, the universe moved closer to the moment when a true star would begin to live. After a very long time being fed inside the gas cloud, the seed of a star at the center had grown far larger than it had been at the beginning. Hydrogen and helium continued to fall inward, slowly, layer after layer. Each layer of gas that sank down made the core a little heavier, a little denser, a little hotter. From the outside, perhaps nothing seemed remarkable yet. There was no brilliant light. There was no explosion. There was no loud moment announcing that something great was about to happen. But in the deepest part of that cloud, the universe was coming very close to having a true star for the first time. On the outside, the cloud was still dark and vast. But at the center, everything had changed. Matter had been squeezed into a smaller region. The tiny particles inside were moving faster because the temperature was rising. We can imagine this like placing both hands around a soft handful of cotton and pressing it gently. At first, it is fluffy and light, but when it is compressed, it becomes tighter and denser. Inside the first gas cloud, gravity was doing something similar, only on a scale far greater than anything around us. It was pulling matter inward, heating the core little by little, until a new boundary was about to be crossed. A star does not shine because it burns like wood, coal, or a candle. Fire on Earth needs air and fuel. But deep inside a star, light comes from something different. When the core becomes hot enough and dense enough, the smallest parts of hydrogen are forced very close together. Normally, they do not combine easily because they tend to push away from one another. But when the temperature becomes extremely high, they move very fast. Some particles come close enough to merge, forming helium and releasing energy. This way of creating energy is called nuclear fusion. In the simplest words, nuclear fusion is the moment when hydrogen in the core of a star begins to become a source of energy. Before that, the seed of the star had mainly heated up because gas was falling inward and being compressed. It was like a kitchen that already had wood and a little warmth, but the main flame had not yet caught. But when hydrogen begins to merge and release energy, that kitchen is no longer merely warm. It truly has fire. From that moment on, The seed is no longer only a growing protostar. It begins to become a star. That first light does not need to feel violent in our imagination. It can be felt like a very distant lamp being turned on after a long night. In the ancient darkness, where starlight had never existed before, a new source of light began to feed itself from within. Hydrogen fused, energy was born, heat slowly moved outward, and light began finding its way through the layers of gas still surrounding it. The universe had prepared for this moment in silence for a very long time, and then, finally, it had its first star. What is most beautiful here is that the star began to find balance. Gravity was still pulling everything inward, trying to squeeze the core smaller, but the energy created inside pushed outward, helping the star resist collapse. We can picture it like someone holding a pillow tightly, while a gentle warmth inside the pillow pushes back. When the two sides hold each other in just the right way, the star can remain stable for a time. It does not collapse immediately, and it does not scatter apart immediately. It begins to live. The first stars may have been very different from our Sunday. Many scientists think they may have been larger, hotter, brighter, and much shorter-lived. But in this first moment, we do not need to go too deeply into the numbers. What matters is this: from a dark cloud, the universe had created a new source of light. Before this, the ancient light was only a leftover trace from the very early universe. But now, light was being created inside a new object in one specific place, deep within a cloud that had once been cold and dark. We can pause for a moment to feel what that means. Long before Earth existed, before there were oceans, before there was the familiar night sky, there was a moment like this somewhere in the young universe. No one stood nearby to see it. No living thing gave that star a name. No eyes looked upward and called it light. But the light was still born. It did not need a witness in order to be real. It only needed enough matter, enough heat, enough time, and a core of hydrogen that had finally begun to create energy. From the moment the newborn star began to shine, the region around it also began to change. Its light and heat touched the remaining gas in the cradle that had formed it. The layers of gas close to the star warmed up. Some of that gas may have been pushed farther away. Some of it may still have been pulled back in. The cloud that had once fed the seed of the star was now beginning to be changed by its first child. It is a beautiful image, a star born from the darkness of a cloud, and then, as it shines, beginning to change the darkness around it. This light also carried a meaning larger than its appearance. It showed that the universe had entered a new stage. Before this, matter had mainly gathered, collapsed inward, and heated up. Now, part of that matter could shine from within. Hydrogen was no longer only gas drifting through space. It had become the fuel of a star. From the simplest ingredient, the universe had created a true lamp. If we compare it to a dark room, this was the moment when the first lamp was switched on. Before that, the room had been preparing for a very long time. The fog had cleared, the floor had grown still, the materials had been gathered. Everything seemed quiet, but inside, the work had happened step by step. Then, in one very distant corner, a point of light appeared. It did not make the whole room brilliant at once, but with just one point of light, the darkness was no longer absolute. In the real universe, the light of the first star may not have spread easily right away. It still had to pass through the gas surrounding it. Some of the light may have been trapped, absorbed, or weakened, but the important thing had already happened. A new source of light had been born. Not light left over from the Big Bang, but light created by a star from its own core. When we look back at the whole journey, we can see that this moment did not appear suddenly. First, there were slightly denser regions in the young universe. Then dark matter created places with deeper gravity. Hydrogen and helium fell into them. Gas clouds formed. Their central regions collapsed inward, heated up, and became protostars. And finally, when the core became hot enough and dense enough, hydrogen began to fuse into helium, releasing energy. Each step may seem small on its own, But when connected together, they become the story of the first starlight. What makes this moment so moving is not its violence. It is moving because it shows us that light can be prepared inside darkness for a very long time. A place that seems silent may still be changing. A cloud of gas that seems invisible may still be nurturing a star. A small hot core in the middle of vast space can become the beginning of an entirely new age. Somewhere in the young universe, the first star began to live in this way. It shone into the gas around it. It warmed the nearby space. It opened the path for other stars that would come later. And even though that first star may have disappeared a very long time ago, its meaning remains. Because after it, the universe was no longer only a place of darkness and preparation. The universe had starlight. We can keep one quiet image in mind: an ancient cloud of gas, a hot core at its center, and the first light beginning to leave the place where it was born. It did not need to be loud in order to be miraculous. It only needed to shine. And when it shone, the universe crossed a very deep boundary, from a place without stars into a place that had learned how to create light. From here, the story would never be the same again. The first star would shine into the gas cradle that had given birth to it. It would change the region of space around it. Later, as more stars appeared, the ancient darkness would gradually gain more and more points of light. But in that first moment, we only need to rest with one simple truth. In a young and quiet universe, hydrogen had begun to become light, and the first star had truly been born. The first star had lit up, but it was not like the familiar sun we see every day. The sun gives us a feeling of stability, warmth, and closeness. It rises in the morning, sets at the end of the day, and in everyday life, we almost take its light for granted. But the first sources of light in the universe were probably very different from that gentle feeling. They were born in an extremely early age, when the universe was still poor in complex matter, with no rocky planets, no mineral-rich dust, and no older generations of stars to leave traces behind. Our sun was born much later. Before the sun appeared, many other stars had already lived and died. In that process, they created heavier elements and returned them to space. Because of that, the cloud that gave birth to the sun contained not only hydrogen and helium, but also carbon, oxygen, silicon, iron, and many other materials. Those materials would later become rock, water, air, planetary cores, and even the elements found in living bodies. In that sense, the sun is a star born in a universe that already had memory. The first stars, however, had almost no memory to inherit. Before them, there were not many stars to create carbon, oxygen, or iron. The space around them was mostly hydrogen and helium, the two lightest elements. In simple terms, they were born from the first and most primitive ingredients. There was no ash from older stars mixed in. There was no rich layer of material like the kind found in star-forming regions today. They were like the first fires lit in a world that was still very new. In everyday life, when we say metal, we usually think of iron, copper, gold, or silver. But in astronomy, scientists use the word more broadly. Any element heavier than hydrogen and helium may be called a metal. Before holding on to the term too tightly, we only need to understand that these are more complex elements, created mostly through stars. Because the first stars were born before the universe had many of these elements, scientists say they had almost no metals. That absence made the way they formed different from many later stars. In modern gas clouds, dust and heavier elements help gas cool down more easily. When gas cools well, it can break apart into many smaller pieces and create many stars of different sizes. But in the first universe, gas had a harder time cooling. It often had to gather into larger masses before it could collapse deeply enough. For that reason, many models suggest that the first stars may have been very massive, many times larger than the Sunday. There is no need to force the listener to remember numbers. We only need to hold on to this feeling. The sun is like a steady lamp in a familiar home. while many of the first stars may have been more like greater torches, hotter, brighter, and more powerful, but burning through their lives more quickly. They were not the kind of gentle light meant to warm a blue planet resting nearby. They were powerful sources of light in a universe that had never had stars before, like the first calls breaking a very long silence. One thing that may sound a little surprising is that a larger star does not necessarily live longer. We might think that having more fuel would mean lasting for more time. But with stars, greater mass usually means the core is squeezed more strongly, becomes hotter, and runs its inner reactions faster. It is like a very large fire. There may be more wood, but it also burns more intensely, so it can run out more quickly. The sun uses its fuel fairly slowly, so it can live for billions of years. But the first stars, if they were very massive, may have shone brightly for a much shorter time than the Sunday. Their light was not only something to be seen, it carried powerful energy, able to heat and change the gas around it. Before stars were born, the gas cloud was like a dark cradle collapsing inward. After a star began to shine, that very light started to act back on the cradle that had formed it. Gas near the star was heated. Some of it may have been pushed away. Some of it may still have been pulled back in by gravity. From a place that had once been quiet, the surrounding environment began to become more active. Imagine listening to this story at night. We do not need to picture it as a chaotic explosion. We can simply imagine a dark region of space, extremely far away, and then a young source of light beginning to shine outward. That light entered the gas around it and changed that region so it was no longer the same as before. It is like turning on a small lamp in a cold room. The room does not change completely at once, but the feeling is already different. The darkness no longer keeps its old shape. The first stars, then, were not only points of light. They were the first sources of energy that made the universe begin to respond. Their light heated gas. Their heat changed the environment around them. And later, when they reached the end of their lives, they could return new elements to space. From that point on, the universe would not remain forever as simple hydrogen and helium. It began to gain new materials for the generations of stars that would come next. Scientists call this ancient generation of stars population 3 stars. Before the name feels too heavy, we can understand it simply. It is the name given to the first, or among the very earliest, stars born from almost primordial gas. The label 3 may sound strange, because we might think the first generation should be called number I. But the history of star classification does not follow that intuition. Younger stars that are richer in heavier elements, like the Sun, are placed in population I. Older stars, with fewer heavy elements, are population 2. And the earliest group, almost without metals, is called population 3. The name may sound dry, but the meaning behind it is beautiful. Population 3 is the way humans name the lamps that opened the path for the universe. They were born before space had many complex materials. They did not inherit what older stars had left behind, because almost no older stars had existed before them. But they themselves became the first generation to leave something behind for the future. From here, the story is no longer only about light. It is also about material. Inside stars, hydrogen can gradually create helium, and later in the lives of massive stars, more complex elements can form. When a large star dies, it may explode or collapse, depending on its mass and structure. If it explodes, new elements are scattered into space, mixing with other gas clouds. Later, those clouds can give birth to the next generation of stars with richer ingredients. From a very familiar point of view, we could say the first stars were like the first workers in the workshop of the universe. They did not have many materials to begin with, but through their lives and their endings, they created new materials. Those materials did not immediately become Earth or life. That required much more time, many more generations of stars, and many more cycles of gathering and scattering. But that path needed a beginning, and the first stars were part of that beginning. The difference between them and the sun also helps us see that the sun is special in its own way. The sun was not the first source of light. It is a later-born star, formed in a universe that had become richer and layered with more history. In the light we receive every day, there is a very long past behind it. Ancient stars that created materials, clouds that mixed elements together, and finally, a more stable star system that could be born. The sun is gentler because it belongs to a different age, a universe that was no longer as primitive as before. The first sources of light may not have been suitable for nurturing a world like Earth. They were too hot, too powerful, and perhaps too short-lived. But that does not make them less important. They were not stars for life to rest beside. They were stars that opened the way. They turned part of the primordial gas into light, and then began to bring new elements into the long story of the universe. There is a very quiet beauty in this. The things that live the longest are not always the ones that leave the deepest influence. Some stars may have existed for only a short time compared with the age of the universe, yet their light and their deaths changed everything that came after them. They were like torches lit on the first night, burning strongly, going out early, but leaving embers for other fires. So when we think about the first stars, we should not imagine them as second versions of the Sunday. They belong to a different time. They were born from simpler gas, and they may have been larger, hotter, brighter, and shorter lived. They did not stand in the sky of any living creature. No eyes looked at them with familiarity. But they did something profoundly important. They opened the age of stars in the universe. Their light was the light of a beginning. Not gentle sunlight on the surface of the sea, not morning light falling through a window, but the first light of matter learning to shine from within. It heated the gas around it, changed the cradle that had given birth to it, and prepared the way for later generations of stars with richer materials. From those sources of light, the universe began to move beyond its original simplicity. If we pause at the end of this path, we can feel something very gentle. Our sun did not appear from an empty story. Before it, other stars had opened the way. Before Earth, ancient sources of light had created the materials for rock, water, and air. Before the night sky that human beings would one day see, there was a time when the sky had no constellations at all, only the first stars beginning to turn darkness into history. The first stars were not like the sun, and that is exactly why they are worth remembering. They belong to a time when the universe was young, primitive, poor in elements, poor in structure, but full of possibility. From hydrogen and helium, they created light. From light, they changed the gas around them. From their brief lives, they left the first step toward the richness that would come later. And a very long time after that, in a quieter corner of the universe, the sun could finally be born. After the first star turned on, the darkness around it was no longer completely the same. Its light did not remain still inside the star. It began to leave the place where it was born, passing through the cold gas around it, touching the hydrogen atoms that had quietly drifted through the universe for a very long time. A small point of light in the middle of the ancient night had begun to change the region of space around it. Before that, most of the hydrogen in the universe was in a fairly stable state. Each atom was like a small closed structure, with its electrons still attached around the center. But the light from the first stars could be very powerful, especially the light from hot stars. When a ray of light with enough energy struck hydrogen, it could knock the electron away from the atom. This process is called ionization. In simpler words, ionization happens when light is strong enough to make a hydrogen atom lose its electron. The atom does not disappear, but it is no longer in the same state as before. And when this happens to many atoms around a star, the entire region of gas begins to change. It becomes hotter, more active, and no longer the quiet layer of gas it had been before starlight appeared. The kind of light capable of doing this is usually light that human eyes cannot see, stronger than the violet part of the familiar rainbow. On Earth, the sun also gives off some of this kind of light, and we know it through the way sunlight affects our skin. In astronomy, this kind of light is called ultraviolet light. Because the first stars may have been extremely hot, their ultraviolet light could have been much stronger, powerful enough to deeply change the hydrogen around them. At first, this change happened only around each source of light. Imagine a very large, very dark room. When one small lamp is turned on, the whole room does not become bright right away. But around the lamp, the darkness has already thinned. The air nearby feels different. The things closest to the source of light begin to appear first. In the young universe, it was the same. Each of the first stars created a region of influence around itself, where hydrogen gas was heated and ionized. Then, over time, more stars appeared. The first small galaxies also began to have light of their own. Each source of light created a small region of change inside the vast sea of hydrogen. One region here, another region there. They did not make the universe blaze with light in a single moment, but they opened scattered patches of brightness, like pieces of dawn slowly appearing across a very long sky. As many regions of gas were changed by light and gradually expanded, the universe entered a larger stage. Earlier, hydrogen had become neutral atoms after the universe cooled. Now, light from the first sources was separating electrons from hydrogen again across a wide scale. For that reason, this stage is called reionization. The name may sound dry, but the feeling behind it is beautiful. It was the time when the first starlight began to thin the ancient darkness. We can think of this process as a very slow dawn, not a dawn on Earth, where the sun rises and the sky changes color in a few minutes. This was a dawn stretching across enormous spans of time, star by star, cluster by cluster, small galaxy by small galaxy, each added its light. Region by region, hydrogen was heated. Piece by piece, the darkness was gradually divided by new sources of light. The important point is that the first stars were not beautiful only because they shone. They mattered because their light had an effect. They were born from hydrogen gas, and then they turned back and changed that very gas. They were nurtured in darkness, and when they became strong enough, they began pushing that darkness a little farther away. Not through noise, but through light, heat, and energy spreading step by step. So, after the first star was born, the story of the universe was no longer only the story of a single point of light appearing in the night. It became the story of light spreading outward, touching matter, turning a quiet region of gas into a warmer, brighter, more active place. From the small changes around each star, the universe began to leave the dark ages in a way that was very slow, very vast, and very deep. At the end of this part, we only need to keep one gentle image in mind: a young star in the ancient universe, its light moving through the hydrogen around it, changing that region of gas. Farther away, darkness still remained. But around the star, one small area had become less cold, less still, less dark. And as more small areas like that appeared, the first dawn of the universe began to spread. The light of the first stars did not only open a very slow dawn for the universe, it also began another story, deeper and quieter in its own way, the story of stellar death. That may sound sad, but in the universe, the death of a star is not only an ending. Sometimes, it is the way matter is returned to space, the way new elements are scattered outward, and the way later generations of stars receive richer material from which to form. The first stars may have lived very differently from our Sunday. Many models suggest that some of them were extremely massive, extremely hot, and extremely bright. The heavier a star is, the more strongly its inner core is usually squeezed. The temperature becomes higher, reactions in the core happen faster, and fuel is used up more quickly. This may feel opposite to everyday intuition, because we often think that more fuel should mean a longer life. But with massive stars, everything is more like an intense fire. It has a lot of wood, but it burns so fiercely that it runs out sooner. Our sun can shine steadily for billions of years. Many very massive stars, however, may live for only a few million years, or a few tens of millions of years. Compared with a human life, that amount of time is still impossible to fully imagine. But compared with the history of the universe, it is a short life. The first stars, if they truly were as massive as many models suggest, may have appeared, shone with great power, changed the gas around them, and then quickly reached the final stage of their lives. Throughout its lifetime, the core of a star is like a very hot furnace. At first, hydrogen is the main fuel. Hydrogen fuses into helium and releases energy, allowing the star to shine. But with large stars, the story does not stop there. As hydrogen in the core gradually decreases, the star may continue creating heavier elements in later stages. Before using more complicated terms, we can understand it simply like this. Inside a massive star, matter can be cooked into heavier forms, like in a cosmic kitchen that is extremely deep and extremely hot. Because of this, the first stars were not only sources of light. They may also have been the universe's first furnaces. Before them, space was almost entirely hydrogen and helium. After they lived and changed the matter inside their cores, new elements began to appear. Carbon, oxygen, silicon, iron, and many other elements did not naturally exist in large amounts from the beginning. They needed the extreme heat inside stars, or the violent moments when stars ended, to be created and released. But a star cannot keep its balance forever. For most of its life, it exists because of a very special balance. Gravity pulls everything inward, trying to squeeze the star smaller. Energy produced in the core pushes outward, helping the star resist collapse. We can imagine it like two hands holding a pillow from opposite sides. One side presses inward, the other pushes back. When these two tendencies balance each other, the star can remain stable. Near the end of its life, that balance begins to weaken. The fuel in the core changes. The reactions producing energy no longer support the star the way they once did. In a very massive star, the core may be pulled downward by gravity and collapse very quickly. The outer layers, once held in place by the structure of the star, also enter a violent transformation, and in many cases, the star does not fade gently like a candle. It ends in an extremely powerful explosion. Before naming it, we can picture it this way. A massive star has reached the end of its life, the inside collapses, and the outer layers are blasted out into space. Matter that once lay inside the star is thrown outward. Light erupts so strongly that, for a short time, the dying star may shine far brighter than it did before. This event is called a supernova. A supernova is not only a beautiful explosion in astronomical images, it is one of the important ways the universe spreads new material into space. Elements created inside the star, or during the explosion itself, can be blown outward. They mix into nearby gas clouds. Much later, those clouds may collapse to form new stars. And unlike the first generation, later stars will no longer be born from almost purely primordial gas. They will contain a little ash from the stars that died before them. There is a deep beauty in this. The first star was born from the simplest ingredients, and then, during its brief life, it created richer materials. When it died, it did not simply disappear. It returned part of what it had made back into space. From a lonely source of light, it became the first sower of seeds for later generations of stars. Still, we need to speak carefully. Not every first star necessarily ended in the same way. Some very massive stars may have collapsed strongly and left behind black holes. Before naming them too heavily, we can understand a black hole as a region with gravity so strong that even light cannot escape once it gets too close. Some stars may have thrown material outward with great force. Others may have kept more of their matter during collapse. Scientists are still studying how the first generation of stars usually ended because they are too distant and too ancient to observe directly with ease. No matter how they ended, their lives still changed the universe. If a first star exploded, it scattered new elements around it. If it collapsed into a black hole, It may have left behind a seed for larger black holes later on. And if many first stars appeared in many different places, each death, each explosion, each collapsing core added a new trace to the larger story. We can imagine a dark room after the first lamp has burned brightly and then gone out. While that lamp was shining, it made the room less dark. When it went out, it did not return the room to exactly the way it had been before. It left behind warmth. It changed the air around it. Perhaps it left a little ash, a small trace, some material for the next flame. In the universe, the death of a star can carry that same meaning, not only closing one stellar life, but preparing for the next one. The first heavy elements scattered outward did not change the universe all at once. After one explosion, Earth or rocky planets did not immediately appear. Much more time was needed. Gas clouds had to mix with new materials. Other generations of stars had to be born. Regions of matter had to gather and collapse again and again. But from those first elements, the path toward richness had opened. Before this time, the universe was like a story written with only a few first letters: hydrogen, helium, light, gravity. After the first stars, that alphabet began to gain new characters. Carbon could later become part of living bodies. Oxygen could later exist in water and air. Silicon could later help form rock. Iron could later lie inside planetary cores or in the blood of living creatures. All of this was still very far away, but the first steps began with the lives and deaths of stars. This makes a supernova more than an explosion. It is like an act of giving back. The star borrowed hydrogen and helium from the young universe. It lived through them, transformed them, and when it could no longer hold itself in balance, it sent some of its new material back into space. Its death created a chance for other clouds to become richer, cooler, easier to turn into stars, and eventually capable of forming more complex star systems. If the listener is lying quietly in the night, this can be felt through a very familiar image. A candle burns in a dark room. While it burns, it gives light. When it goes out, it leaves behind the scent of wax, a little warmth, and the trace that it was once there. A massive star is completely different from a candle in scale, but the feeling of leaving a trace can help us understand. It does not pass through the universe leaving nothing behind. It lives, it shines, it changes matter, and then it leaves new seeds for the future. The first stars were therefore both brilliant and brief characters in the story of the universe. They were born from darkness, shone powerfully, changed the gas around them, and may have ended in violent events. But that violence was not only destruction. It was also construction in another form. From the layers of matter thrown outward, the universe began to gain materials for things that could not have existed before. After the deaths of the first stars, the surrounding gas clouds were no longer exactly as they had been at the beginning. They had been mixed with a little heavier material. They carried traces of light, heat, and explosion. As those clouds continued to move, mix, and collapse, they could give birth to new stars with different ingredients. Later generations of stars would not begin from nothing. They would receive part of the legacy of the first stars. Perhaps this is one of the most beautiful meanings of the story. The universe does not simply light up and then go dark. It learns how to keep traces of what has happened. A star dies, but its matter does not vanish. It becomes part of the surrounding space. Then, much later, that material may enter another star, another planet, or another world. The ending of one object can become part of the beginning of another. We can look at the first stellar explosions with a gentler feeling. They were not only violent scenes in the far distance, they were the way the universe began to enrich itself. From simple hydrogen and helium, the first stars created new elements. From their deaths, those elements were scattered into the darkness. And from that darkness, now seeded with new material, later generations of stars would have more conditions to be born. The first light, then, did not end when a star went out. It continued in what the star left behind. It continued in the enriched cloud. It continued in new generations of stars. And much later, it continued in planets, oceans, atmospheres, and eyes that could look up at the night sky and wonder how everything began. From a first star that lived quickly and died powerfully, the universe received an early gift: richness. Not complete richness right away, but the seed of it. A little carbon, a little oxygen, a little silicon, a little iron. Those small materials would drift through time for an unimaginably long while, but eventually they would become part of much larger stories. So the death of the first stars was not only a final period, it was like a breath returned to space. One source of light left, but it left behind material for other sources of light. One star ended, but the universe did not become poorer. On the contrary, it began to grow richer. From the first stellar explosions, the darkness gained not only more light, but also more ingredients, so that, one very distant day, worlds like ours could be born. After the first stars began to shine, the universe was no longer only a vast darkness with a few lonely points of light. In many places, other gas clouds continued to collapse inward. One star was born, and then perhaps a few more appeared nearby. They did not rise all at once like lights in a city. They appeared scattered and slowly in regions with enough gas and enough gravity. But once many points of light began to gather closer together, the universe entered something new. Light was no longer completely alone. Before we call something a galaxy, we only need to understand it simply like this. If a star is like a lamp, then a galaxy is like a very large place that holds many lamps together. Inside it, there are stars, gas, dust, and also invisible matter that helps create gravity. All of these things do not immediately fly apart, because gravity holds them within the same system. A large system like this is called a galaxy. Our Milky Way is also a galaxy. But the first galaxies certainly did not look like the Milky Way today. They were not vast, stable, and beautifully shaped like mature galaxies. They may have been much smaller, much more primitive, and far more chaotic. Inside them, gas was still falling in, new stars were still forming. Some massive stars lived quickly and died early, changing the environment around them. So the first galaxy was not like a completed home. It was more like the first house being built in the dark. For the first galaxies to appear, the universe had to move through many small steps. First, there were regions of matter that were slightly denser than others. Those regions pulled in more gas. The gas gathered into clouds. Inside those clouds, some hot cores formed and became stars. When many stars were born within a larger region, they began to create the first clusters of light. From those clusters, small systems gradually appeared. These small systems could grow by collecting more gas or by joining with other systems. Before using the word merger, we can understand it as many small pieces coming together. One small group of stars meets another group. A large region of gas falls into a region that already contains stars. Two small systems move closer together, and then gravity holds them within a larger shared system. The process where smaller structures combine to form larger structures is called a merger. Imagine a dark stretch of land where, at first, only one house has a light on. Later, a few more houses nearby begin to shine. Then more small lights appear. Looking from far away, we no longer see only one point of light, but a small village beginning to form. The young universe was much the same. From one star, then many stars, then star clusters, light began gathering into places with clearer shapes. That was the first step on the path toward forming galaxies. Gas still played a very important role in the first galaxies. Gas is the raw material for making new stars. Wherever a great amount of gas gathers, more stars can be born. But the gas inside young galaxies did not stand still. Starlight heated it. Stellar explosions could push some of it outward. Later, other gas could fall back in. Inside those young systems, everything was still changing. The first galaxy was not a still picture, but a place growing into itself. This growth does not need to be explained too complicatedly. We only need to remember that the universe did not create a complete Milky Way from the very beginning. It began with much smaller systems. These small systems had gas, a few young star clusters, and gravity holding them together. Then, over time, they made more stars, gathered more matter, and sometimes merged with one another. Step by step, the first galaxies became clearer. One beautiful thing is that a galaxy does not only hold stars together, it also holds traces of what has happened. When a massive star dies, it can scatter new elements into the gas around it. Those elements mix into the clouds inside the galaxy. Later, from clouds enriched with that material, new stars can be born. So a young galaxy is like a place that keeps the first memories of light, which stars lived, which stars died, and how matter changed. The first galaxies may have been small and faint, but their role was enormous. A single star affects only a small region around it. But a young galaxy, with many stars inside, can send light much farther. It heats the gas around it. It helps the universe move away from the dark ages. It also creates more places where new stars can continue to form. From a few points of light, the universe began to have its first islands of brightness. We should picture those islands gently. They were not yet like the beautiful galaxies we see in telescope images today. They were still small, still faint, still colliding and changing. But that unfinished state is exactly what brings them close to the feeling of a beginning. They were like the first rooftops in a land that was still dark. Inside them were young lights, moving gas, traces of stellar explosions, and gravity quietly holding everything together. Our Milky Way also has a very long past like this. It did not appear at the beginning in its present form. It grew through many rounds of gathering matter, forming stars, and merging with smaller systems. When we look at the Milky Way in the night sky, we are looking at a galaxy that has matured through countless changes. But deep in the past, that path began with systems that were small, faint, and very young. So the first stars were not only the opening points of light, they were also the first bricks used to build galaxies. From stars came star clusters. From star clusters came small systems. From small systems, larger galaxies gradually formed. Everything was connected by gas, gravity, light, and time. If we settle into that image, we can feel the ancient darkness beginning to give light places to gather. The small points of light were no longer completely alone. They were held within larger regions of matter, like tiny lamps in a very distant village. The first galaxies appeared slowly, not yet large, not yet stable, but already enough to give light its first home in the universe. From the first few stars, the universe began building its first bright islands. And from those islands, much later, great galaxies like the Milky Way could finally be born. After the first sources of light, the universe did not only gain starlight. It also began to carry the traces left behind after some massive stars reached the end of their lives. Some stars were born with great power, shone intensely, used their inner fuel at a tremendous rate, and could not remain for as long as our sun day. To human beings, their lifetimes would still be almost impossible to imagine. But compared with the age of the universe, they may have been brief. They arrived, lit up the gas around them, and then left something behind. A star lives because of balance. Inside it, energy produced in the core pushes outward. Gravity pulls everything inward. We can imagine it like a tent held tight from two sides. If the forces hold each other just right, it stands. But when a massive star reaches the end of its life, the fuel in its core can no longer support it as well as before. The deepest part begins to be pulled inward more strongly. For a very heavy star, that contraction can become extremely deep and extremely fast. When too much matter is squeezed into a very small region, the gravity there becomes so strong that even light cannot escape if it gets too close. Before naming this phenomenon, we can understand it simply. It is a deep region of gravity where anything that comes too close has great difficulty getting back out. A region like this is called a black hole. The name black hole may make listeners think of something frightening. But in this story, we can look at it more gently. It is not a giant mouth swallowing the entire universe. It is simply the natural result when a very massive star collapses after it can no longer hold its balance. If you are far enough away, it does not pull everything in through some strange force. It only has gravity like a very heavy object. What makes it special is the region very close to it, where light cannot escape and return to us. Some of the first stars may have left behind black holes like this. They were like the very deep remains of a source of light that once existed. The star before it had shone, warmed the gas around it, and perhaps helped create new elements. Then, when it ended, it did not completely disappear from the story. It may have left behind a gravitational seed, much smaller than the enormous black holes inside mature galaxies, but still important enough to begin another journey. We can imagine this like a piece of coal left after a fire has gone out. The flame is no longer shining, but the coal is still a trace of the old heat. If there is more fuel and the right conditions, it can become part of a new fire. A black hole left behind after one of the first stars carries a similar feeling. It does not shine like a star, but it remains there, quietly, with its gravity, inside a universe that is still growing. In young galaxies, there was still a great deal of gas. If a black hole lay in a region rich with gas, the surrounding matter could slowly fall toward it. The black hole itself does not release light from within, but the gas outside it, before falling too deeply, can spin very fast, heat up, and glow. In simpler words, we do not see the darkest part of the black hole itself. We see the matter around it heating up as it is pulled inward. This point makes black holes a little easier to picture. A star shines because its core creates energy. A black hole does not shine in that way, but the gas falling around a black hole can glow intensely. It is like the wind. We do not see the invisible hand of the wind itself, but we see leaves moving because of it. With black holes, it is similar. Often, what we observe is not the black hole itself, but its effect on the matter around it. The first small black holes may have been seeds for larger black holes later on. If they continued to take in gas, they grew. If two small galaxies merged, the black holes inside them could also move closer together and eventually combine. Not every seed becomes a giant. Not every black hole grows in the same way. But if some of them had enough material and enough time, they could become part of the story of the enormous black holes found at the centers of later galaxies. Scientists are still studying how that path unfolded. Some black holes may have begun from the deaths of very massive first stars. It is also possible that, under special conditions, a large cloud of gas collapsed directly, creating a heavier black hole seed from the beginning. Before remembering the name, we only need to understand the idea. Some gas clouds may not have broken apart into many smaller stars, but instead fallen inward very quickly and formed a larger black hole. This way of forming is called direct collapse. We do not need to choose one single answer right away. The early universe may have used more than one path. Some black holes came from dead stars. Some may have come from large gas clouds collapsing straight inward. What matters is that after the first stars were born, the universe did not only gain light and new elements, it also began to contain very deep regions of gravity, the first black hole seeds, lying quietly inside young galaxies. The story therefore becomes wider, but still very natural. A gas cloud creates a star. A star shines. If that star is massive enough, when it ends, it may leave behind a black hole. From the same original material, the universe creates both light and deep dark regions. These two things may seem opposite, but they belong to the same flow of development. Matter gathers, heats up, shines, and then leaves behind new structures for the future. In a young galaxy, we can imagine that scene quietly. A few young stars are still shining. Clouds of gas are still drifting and falling into regions with stronger gravity. Somewhere, after the death of a massive star, a small black hole remains. It is not loud. It does not shine like a star. But around it, gas can spin, heat up, and release light before falling deeper. Even the darkest thing can make the region around it shine in its own way. This does not make the story frightening. On the contrary, it gives the universe more depth. The first stars did not only begin the story of light, some of them also left behind seeds for great mysteries that would come later. A black hole is not separate from the story of stars. It can be the final trace of a star that once shone with everything it had in the young universe. If we settle into that image, we can feel something very soft. The universe does not lose what has happened. A star goes out, but its matter and gravity still leave a trace. Light may depart, but a deep region remains behind. That deep region can continue pulling in gas, heating it, and taking part in the growth of a young galaxy. The ending of a star, then, is not only an ending, it can also be another way for the story to continue. From the first sources of light, the universe began learning how to create many things at once. It had young stars, enriched gas, small galaxies still growing, and the first black hole seeds. Each held its own role. Stars brought light. Stellar explosions brought new elements. Black holes brought deep centers of gravity, places where matter could fall inward and change the environment around them. Somewhere very far in the past, perhaps one of the first black holes was lying inside a small galaxy. It was the remains of a star that no longer shone. Around it, gas still moved. Farther away, other stars continued to shine. That young system was not yet complete, but it already carried many pieces of the later universe within it. Light, gas, ash, gravity, and very deep dark regions. The first black hole seeds, then, do not take away the beauty of the story of starlight. They make that story more complete. Because the first light did not leave only light behind, it left material, motion, new structures, and sometimes even regions from which light could not escape. From that point on, the universe did not only become brighter, it also became more complex, deeper, and more prepared for the larger galaxies that would form over billions of years. After moving through the first light, the first stars, the first small galaxies, and even the first black hole seeds, a very natural question may arise. If they are so important, why do we not simply use a powerful telescope to photograph them? Why not point Webb, or some other large telescope, toward the ancient universe and look directly at the first star? That question sounds very simple and very human. When we want to know whether something is real, we often want to see it. A photograph always gives a stronger feeling of certainty than an explanation. When we see the moon, we believe it is there. When we see Jupiter, we feel that it is a real world. But with the first stars, the story is far more difficult. They are not only far away. They are far away in a way that almost goes beyond every familiar feeling we have. Light needs time to travel through space. When we look at the moon, we see it as it was a little more than 1 second ago. When we look at the sun, we see light that left the sun about 8 minutes earlier. When we look at a distant star, we may be seeing light that has traveled for tens, hundreds, or thousands of years. But with the first stars, their light would have had to travel through almost the entire history of the universe to reach us. They belong to a very early time, when the universe was far younger than it is now. The first problem is distance. A star, even if it is very bright, is still tiny if it is placed near the edge of the observable universe. It is like trying to see a very small lamp on the other side of an ocean, while between us and that lamp there is fog, waves, wind, and many other lights. Even the most powerful telescopes cannot easily separate a single star from such an ancient time. Often, what we see is not one star, but the combined light of an entire very young galaxy. This is very important. The first stars may have existed inside gas clouds or small star systems that were still forming. From Earth, the light of many stars, hot gas, dust, and other sources of light can all blend together. It is like standing very far away and looking at a city at night. We may see a glowing region, but it is difficult to know exactly where each individual lamp is, which one turned on first, which one shone more strong. The second problem is time. The first stars may have lived very short lives if they were truly very large and very hot. A heavier star usually uses its fuel faster. It may shine brilliantly, but it does not remain for long. So even in the early universe, the chance of catching one of the first stars while it was still alive was not easy. Many stars may have been born, shone, and died before the light from the regions around them could fully tell their story to us. We can imagine it like trying to photograph a flash of lightning very far away, without knowing where it will appear, when it will appear, or how long it will last. If we are a little late, it is already gone. If we look in the wrong direction, we miss it. The first stars were not lightning in the literal sense, but the feeling of observing them is somewhat similar. They are distant, ancient, possibly brief, and hidden in regions that are very difficult to separate clearly. The third problem is that their light has been stretched by the universe along the way. Space does not stand still. The universe is expanding, which means the distances between very far regions grow larger over time. When light travels through expanding space, its wavelength is stretched as well. Before naming this phenomenon, we can imagine a mark drawn on a rubber band. If we stretch the rubber band, the mark stretches too. Light traveling through the universe is stretched in a similar way. When light is stretched like that, it no longer keeps its original form. Light that may once have been ultraviolet, or light visible to human eyes, can be shifted into the infrared range after billions of years traveling through space. Infrared is a kind of light that our eyes cannot see, but specialized telescopes can measure. The phenomenon where light is stretched toward longer wavelengths is called redshift. The name may sound technical, but the main idea is gentle. Ancient light has been stretched by the universe while traveling toward us. This is why, if we want to find the first sources of light, we cannot look only with the kind of light familiar to human eyes. We need telescopes that can see the light after it has been stretched. This is why infrared telescopes are so important. Before remembering the word infrared, we only need to understand that it is light outside the range human eyes can see, but it still carries information. For very distant sources, their original light has often moved into this range before reaching us. Even with the right telescope, another difficulty remains. The universe is not perfectly clean like a freshly washed window. Between us and those ancient sources of light, there is a great deal of matter. There is gas between galaxies. There is dust inside nearer galaxies. There are other sources of light along the same line of sight. Ancient light must pass through all of these layers before reaching a telescope. Along the way, some of it may be absorbed, weakened, or mixed with light from other objects. This is like hearing a very distant bell in a sleeping city. The bell may truly be ringing, but on its way to our ears, the sound is softened by wind, blocked by walls, and mixed with the noise of cars far away. To know where that bell came from, we must listen very carefully. With the universe, it is similar. Scientists do not simply look at a picture. They must read the light, separate a faint signal from many layers of noise, and see whether there are any traces that belong to the first sources of light. Another reason direct photography is so difficult is that the first stars may no longer exist. We are looking for the light of objects that lived in the very distant past. Many of those sources have long since died, leaving behind explosions, black holes, or material mixed into later generations of stars. So sometimes what we search for is not the star itself still shining, but the traces it left behind in the light of ancient galaxies, in the chemical makeup of very old stars, or in the way the universe's hydrogen gas changed over time. This is what makes the story more beautiful, even though it also makes it harder. Science does not always see the main character standing directly before it. Often, science reads footprints. A first star may have disappeared, but if it once created new elements, strong light, or a changed region of gas, those traces may still remain in the universe. Just as we may no longer see the person who crossed a sandy shore, but the footprints still tell us they were there. Scientists use many methods to search for such traces. They look for extremely distant galaxies, because looking farther away also means looking deeper into the past. They analyze the light from those galaxies to see whether there are signs of stars that were very hot, very young, and very poor in heavy elements. They search for places with very few traces of carbon, oxygen, and iron, because the first stars are thought to have formed in environments made almost only of hydrogen and helium. They also observe how ancient light passes through hydrogen gas in order to understand how the first starlight changed the universe. Before calling this spectroscopy, we can understand it simply like this. Light does not only tell us whether something is bright or dark. If we split light into many parts, we can read signs of elements, temperature, and motion inside it. It is like hearing a person's voice. We do not only know whether that person is speaking, we can also sense whether the voice is high or low, near or far, calm or trembling. When scientists split light apart to read the information inside it, they are using spectroscopy. Thanks to spectroscopy, a tiny point of light in an image can become a story. It can tell us how far away the source is, what kinds of gas are present, whether there are many heavy elements, and whether very hot stars may be contributing to the light. So in the study of the early universe, the image is only the first step. What matters even more is what signs the light in that image carries. Still, we need to remain careful. So far, directly confirming one individual first star is extremely difficult. There are candidates, there are signs, and there are very distant galaxies that attract scientific attention. But saying that we have clearly seen a first star the way we see the sun would not be accurate. The truth is beautiful in another way. We are following the extremely faint traces of ancient sources of light, using delicate instruments and the patience of many generations of research. This does not make the story less wonderful. On the contrary, it makes the journey feel more human. We do not stand before the universe like someone turning on a lamp and immediately seeing everything. We are more like someone sitting in the night, listening for a very distant sound, and slowly realizing that it comes from a time that no longer exists. Every photon, every tiny particle of light that reaches a telescope, is a fragment of a letter from the past. It does not tell us everything, but it carries enough signs for us to know that something happened. So, when we ask why we cannot simply take a picture of the first stars, the answer is not that they are unimportant, or that telescopes are not powerful enough in the ordinary sense. The answer is that they are too far, too ancient, too faint, perhaps too short-lived, and their light has been stretched, weakened, mixed, and obscured along the way. To understand them, we do not only need to look, we need to read the light very carefully. There is a quiet beauty in that. The first stars may have gone out a very long time ago, but the universe still keeps a few traces of them. A little stretched light, a little gas that was once heated, a few new elements appearing in later generations, a distant galaxy carrying signs of very young, very metal, poor stars. All of these are like small scraps of paper left behind from an ancient story. When we lie still and think about this, the night sky can begin to feel deeper. The points of light we see today are not only present-day stars. Behind them is a very long history of lights that arrived, departed, and left traces behind. The first stars may not easily appear in a clear photograph, but they are still present in the way the universe has changed. They are present in the light of ancient galaxies, in the enrichment of matter, in the question human beings continue to follow. And because they are so difficult to see directly, the search for them becomes even more like a slow act of listening. We do not rush. We do not need a perfect image right away. We read each layer of light, each small sign, each faint region in the data, because sometimes the first things in the universe do not return to us as a sharp portrait. They return as a very distant whisper, one that must be heard with patience. In the deepest place of the past, The first stars may have shone and then vanished, but their light, or the traces of their light, still guide us, not through a simple photograph, but through fragile pieces of signal that have traveled for more than 13 billion years. And inside those pieces of signal, human beings are still trying to recognize the moment when the universe first had stars. There are some lights that left the places where they were born a very long time ago, so long ago that by the time they reach us, almost everything in the universe has changed. They may have begun in a very young galaxy, at a time before the sun, before Earth, before oceans, before any eyes had ever looked up at the sky. Then that light traveled on through space, crossing more than 13 billion years, until a tiny part of it touched a telescope built by human beings. Along the way, that light did not remain exactly as it was at the beginning. The universe has continued to expand. The distance between very far regions has slowly grown wider, and as light travels through that expanding space, it is stretched along with it. Imagine a small mark of ink on a rubber band. When the rubber band is pulled, the mark becomes longer too. Ancient light behaves in a similar way. It is stretched during its journey. Scientists call this stretching redshift. We do not need to hold on to that name too heavily. We only need to understand that the farther and older the light is, the more it has been stretched. Some light may have been very powerful and very hot when it first left its source, but after more than 13 billion years, by the time it reaches us, it has shifted into a form that human eyes can no longer see. It has not disappeared. It has simply moved into another part of light, beyond the familiar color red. That region is called infrared. Infrared may sound unfamiliar, but it is around us more than we might think. The warmth of the human body also gives off infrared light. Some everyday devices use infrared to send signals. Our eyes simply cannot see it. To recognize it, we need another kind of eye, one that is more sensitive, colder, and specially made for this very faint light. That is why Webb is so important. Webb is not only a large telescope in space, it is like a pair of eyes designed to see the light that human eyes miss. Signals from very young galaxies, from regions of stars so distant that their light has been stretched across almost the entire history of the universe, may now lie in the infrared. And Webb is there, quietly, to receive those weak signals. Each time Webb looks very far away, it is not only looking into a distant place in space, it is looking back into a very old time. Light needs time to reach us. The farther a galaxy is, the longer its light has taken to arrive. So when we see a very distant point of light, we are not seeing it as it is now. We are seeing it as it once was, at the moment its light began to leave. That point of light may be only a tiny red speck in a wide image. At a quick glance, it may seem almost unremarkable. But for those searching for the first dawn of the universe, a faint speck like that can be a doorway. Behind it may be a very young galaxy, a region where stars are forming intensely, or a place that still carries traces of some of the earliest generations of stars. But seeing a point of light is not enough. A point of light is like a voice echoing from very far away. We hear it, but we still want to know what it is saying. Light is the same. It carries signs of the place that created it. What kinds of gas were there? How hot the source of light was? How much the light has been stretched? And whether that place contained many heavy elements or was still very primitive. To read those signs, scientists split light into many parts, much like sunlight passing through a prism and spreading into many colors. This way of reading light is called spectroscopy. In the simplest terms, an image tells us that there is a point of light there. Spectroscopy helps us understand what story that point of light is telling. Thanks to spectroscopy, a faint speck can begin to have a life of its own. It is no longer only a dot in an image. It can tell us, I am very far away. My light has traveled for a very long time. I contain hydrogen. I may contain very few heavy elements. There may be young, hot stars here. Of course, light does not speak in words, but in its faint lines, human beings have learned to read small signs one by one. What we should keep in mind gently is that Webb cannot easily point at one individual first star and say, "This is it." Those stars are too far away, too faint, and may have lived for too short a time. Webb usually brings us closer by finding very young galaxies, very ancient sources of light, and places that may contain the earliest generations of stars. From there, scientists compare, test, and slowly piece the picture together. This search is not loud. It is not like throwing open a door and seeing the entire past in front of us. It is more like sitting in a quiet room, holding a very old letter. The paper has grown thin. The writing has faded. A few lines are no longer clear. But if we read slowly, we can still recognize that someone sent it from a very distant place. Light from the early universe is like that letter. It is no longer untouched as it was when it first left its galaxy. It has been stretched, dimmed, and carried through gas, dust, and time, but inside it, traces still remain. Webb helps human beings recognize those traces, not through haste, but through a very patient way of seeing. Think for a moment about the journey of one tiny ray of light. It leaves an ancient galaxy when the universe is still young. While it is traveling, other galaxies grow. Stars are born and die. The sun forms. Earth cools. Oceans appear. Life begins. Human beings appear, learn to look at the sky, and eventually send a telescope into space. After all of that, the tiny ray of light finally touches Webb's mirror. That moment is quiet, but very deep. The distant past touches the present through a signal so fragile it almost seems unreal. Not an explosion, not a brilliant picture, just a little ancient light. Enough for human beings to keep asking, what was there? Where might the first stars have been? When did the first darkness begin to thin? Webb does not answer everything all at once. It only helps us step closer. A farther galaxy, a weaker infrared signal, a spectrum showing that the light has been stretched greatly, a sign that the place was still poor in heavy elements. Each detail is like adding one more line to an unfinished picture. No single line tells the whole story by itself, but many lines placed together make the first dawn a little clearer. Perhaps that slowness is what makes this story beautiful. Human beings do not stand before the universe as if we already know everything. We stand before it like listeners. We do not force the past to speak loudly. We learn how to hear what remains. A faint point of light, a stretched line of radiation, a very weak infrared signal that has traveled for more than 13 billion years. The first stars may not yet appear before our eyes as a clear image, but their traces may lie in the light of ancient galaxies, in hydrogen gas that was once heated, in the absence of heavy elements, and in the signals Webb is helping us read again. They do not return as a portrait. They return like the remaining warmth of a very old fire. And if tonight we lie still, we only need to keep one gentle image in mind. Somewhere extremely far away, an ancient light has traveled through nearly the entire history of the universe. It reaches us weakly, faintly, almost only as a trace. Webb quietly receives it, and human beings, from a small planet around an ordinary star, begin reading again the story of the time when the universe first had stars. Wonder does not always need to appear clearly. Sometimes, it is only a very small signal, just enough to remind us that before the familiar night sky, before the sun and earth, there were first sources of light quietly opening the history of starlight. After tracing how the first starlight was born, there is still one thing we cannot clearly see: what those first stars were really like. They are no longer there for us to observe directly. Their light has traveled for more than 13 billion years, and many of those stars may have vanished a very long time ago. So what human beings are searching for is not only a photograph, but answers to very specific questions. How large were they? How long did they live? Were they born alone or together? And what did they leave behind after they went out? Perhaps those stars belong to a time before the sun, before Earth, before every ocean, and every sky human beings would ever see. If they were very massive, they may have lived quickly and disappeared long ago. Because of that, we cannot see them the way we see a star shining in the sky today. We can only search for the traces left behind after their light. The first uncertain thing is their size. Many scientists think the first stars may have been much more massive than the Sun, because the primordial gas at that time had difficulty cooling and breaking apart into many smaller clumps. But that does not mean they were all the same. There may have been extremely large, very hot stars that lived very short lives. There may also have been smaller, dimmer stars, harder to recognize in the traces they left behind. The real picture probably did not contain only one kind of star. Another question that remains open is how they were born. A large gas cloud may have created one very massive star at its center, but it is also possible that the cloud split into smaller pieces, allowing several stars to form in the same region. If they were born in groups, their light would have affected the surrounding gas differently than if there had been only one lonely star. So even the question of whether they were born alone or together can change the way we understand the first dawn of the universe. Then there is the way they ended. Some massive stars may have exploded, scattering the first elements into space. Others may have collapsed into black holes. Those endings matter deeply because they determine what the universe received afterward. If there was an explosion, the surrounding space was mixed with new elements. If there was a black hole, a young galaxy may have gained a deep region of gravity that could pull in gas later on. Whether the first stars lived briefly or longer, whether they were lighter or heavier, and how they died all left different traces. But we do not need to let these unknowns feel overwhelming. We can understand it simply like this. Human beings know that the first stars had to come from light gas, gravity, and time. What we are still searching for are the details of the smaller stories inside that larger picture. It is like knowing that a forest grew from its first seeds, while still wanting to know how tall the first tree was, where it grew, and how it scattered new seeds afterward. Because we cannot directly see each of the first stars, scientists search for them through traces. One trace may be found in the light of extremely distant galaxies. Another may be found in hydrogen gas that was once heated by starlight. Another may lie in the composition of very old stars, where a part of the chemical memory from ancient explosions may still remain. Each small trace is like a fragment of a letter left behind from the time when the universe first began to have stars. Webb helps human beings get closer to those traces. It looks into infrared light, where many ancient signals have been stretched after traveling through space for more than 13 billion years. A very faint red dot in an image may not seem impressive to the naked eye, but to scientists, it may be a sign of a very young galaxy. When that light is read more carefully, we can learn how far away it came from, what kinds of gas it contains, and whether that place has many heavy elements or very few. This kind of reading requires a great deal of patience. Science cannot simply look at one point of light and quickly say that it is the first star. Every conclusion must move slowly. The light has to be checked. The data has to be compared with models. Other possibilities have to be considered as well. This caution does not make the story dry. It makes the story more trustworthy. Because when facing a past that distant, the most beautiful thing is not to speak quickly, but to listen correctly. We can imagine this journey as trying to find a very distant bell in the night. The bell rang long ago. By the time it reaches us, the sound has become weak, mixed with the wind, softened by many layers of space. But with ears sensitive enough and patient enough, we can still recognize that the bell was once there. The light of the first universe is similar. It is faint, but it is not completely silent. What makes this story easy to feel is the fact that it remains unfinished. We are not standing before a secret that has been fully closed. We are standing before a door that is still slightly open. Through that opening, we can see part of the past, light gas gathering, stellar cores heating up, the first light appearing, and later generations of stars continuing to make the universe richer. Behind the door, there are still things waiting to be understood more clearly. One day, new telescopes may be able to look even deeper. Weaker signals may be read more clearly. Younger galaxies may be found. Perhaps we will understand better how massive the first stars were, how they lived, and what they left behind after disappearing. But even now, without all the answers, we have already understood the most important thing. The universe was not bright from the beginning. It went through a long period of preparation before the first stars were born. And perhaps that alone is enough to make us look at the night sky with a different feeling. The points of light we see today were not always there. They belong to a very long history, one that began with the first regions of gas learning to collapse under gravity. Before every constellation, before the familiar Milky Way, before the sun, there were the first sources of light opening the way. Far away in the past, a first star once shone. No one saw it. No planet was nearby to receive its light, but it still shone. And even though it vanished long ago, the question of it remains in every faint signal human beings are still reading, in every telescope turned toward the deepest regions of the sky. Now, let us return to the familiar night sky. No telescope is needed, no enormous numbers, and no need to try to imagine the entire history of the universe all at once. Just imagine yourself standing beside a quiet window, looking up at a few tiny points of light far away. To the naked eye, they look only like thin specks of brightness against the dark. But after this journey, we know that each point of light is no longer as simple as it once seemed. It belongs to a very long story, one that began when the universe had no stars at all. There was once a time with no sun, no Milky Way, no constellations that human beings would later name. There were no rocky planets, no oceans, no atmospheres, no life. There was only a very young universe, very wide and very dark, with the simplest ingredients: hydrogen, helium, gravity, and regions of matter that were just a little denser than their surroundings. From those things, which may seem almost too little, the story of the first stars began. The first starlight did not appear like a sudden miracle. Before it came many slow steps. Matter had to gather. Gas had to fall into regions with stronger gravity. Primordial clouds had to collapse inward. Their centers had to heat up. Then, at some point, when the inner core became hot enough and dense enough, hydrogen began to create energy. A true star lit up. No one was there to see it, and no planet was nearby to receive its light. But that moment was still real. The gentlest part of this story is this: the first darkness was not emptiness. It was a place where everything was being prepared. In that darkness, gas was still moving. Gravity was quietly pulling matter closer together. Clouds that had not yet begun to shine were still collapsing inward. Small cores that were not yet stars were slowly heating up. There were stages that, from the outside, may have seemed as though nothing was happening, but inside, the most important things were beginning to form. From the first star, the universe began to change. Its light heated the gas around it. Some massive stars lived very quickly, then ended violently, scattering new elements into space. Those elements did not immediately create Earth or life, but they were the first step toward a universe that was no longer made only of hydrogen and helium. Each later generation of stars received a little more new material, then continued to be born, to shine, and to leave its own traces behind. Much later, from materials created across many generations of stars, larger galaxies formed. New gas clouds gave birth to new stars. One of those stars was the Sunday. Around the sun, matter gathered into planets. On one small planet, water appeared, air formed, life developed, and eventually there were eyes that could look up at the sky and wonder, how did the first light in the universe begin? That question carries us very far away, but it also brings us closer to ourselves. Our bodies are not separate from the story of stars. Carbon, oxygen, calcium, iron, and many other elements were not fully present from the beginning. They belong to the long history of generations of stars that lived and died. The first stars may not have created all of those elements immediately, but they opened the first door. They began the process that allowed the universe to move from simplicity toward richness. So when we look at a star in the sky, we are not only looking at a distant point of light, we are looking at a piece of a very long history. Before today's light, there was the first light. Before mature galaxies, there were young, small galaxies. Before the sun, there were older generations of stars. And before all of those familiar things, there was a very long dark age when matter was quietly preparing for the first birth of starlight. Science helps us understand this without taking away the beauty of the sky. When we know that a star is born from gas collapsing under gravity, it does not feel less miraculous. It feels more real. When we know that ancient light has traveled for more than 13 billion years to reach a telescope, the universe does not feel colder. Time feels wider, and human beings, though small, still seem able to listen to the very distant traces of the past. There are still many things we do not fully know about the first stars. How large they were, whether they were born alone or in groups, how they died, how many new elements they left behind. All of these remain questions under study. But we do not need every answer in order to feel the meaning of this story. The main path alone is enough to make the sky feel different. The universe was dark for a very long time. Then matter gathered, heated up, and the first starlight appeared. Perhaps this is the gentlest thing to leave with. Not everything bright begins in brightness. Some lights need a very long darkness in which to be prepared. Some great things begin with very small movements. A region of gas slightly denser than the rest. A quiet pull of gravity. A cloud collapsing inward. A core slowly heating up. And then, one day, light appears. After the first star, there would be a second star, and then many others. After individual points of light, there would be star clusters, small galaxies, and then larger galaxies. After the first elements, there would be materials for rock, water, air, planets, and life. None of this happened in a single moment. It unfolded across immense time, through many births and endings. But every great journey needs a starting point. For the history of starlight, that starting point was found in the first stars. Now, when we return to the night sky, we can look at those points of light with a different kind of quiet. Each star today is not only an object far away, it is a descendant of an ancient history of light. It reminds us that the universe was not always as bright as we might imagine. It was once dark, simple, and very young. And from that very simplicity, it created light, then created more complex things, until there was a small world able to look back. If you are listening to this story tonight, in a quiet room, let the final image be very light. A young universe, wide and dark, a cloud of gas collapsing in silence, a small core slowly heating at the center, then a first point of light appearing, very far away, very ancient, yet enough to open the history of every starlight that would come after it. And within that very distant light, there is the beginning of the sky we are looking at today.